Hello all and welcome back to this course on digital systems. So in the last lecture we looked in some fair detail the decimal and the binary representation of the same number. We looked at how to convert one from one representation to the other and so on, right? So in this lecture we are going to look at if the it turns out that the binary representation in powers of 2 is not the only useful representation. There are also certain other representations, certain other bases of number systems that are very useful for us to deal with. Okay, so let us look at uh, a general a general base or number system. Okay, so what we mean here is the decimal number, let's say a number d in base 10 can be represented, of course, in base 10 as k equal to 0 to how many ever digits, right? Let's say nd minus 1, okay, uh, 10 power k into let me call it dk because it's the decimal number system, right? Now I could represent the same number in any arbitrary base, okay, and most importantly dk is element of 0, 1 all the way to 9. It has to be one of the decimal numbers from 0 to 9, right? Now on the other hand, the same decimal number in base 10 can be represented as in base r 0 to n r minus 1 r power j into this is this is base r, so it's not, let me just call it aj. Okay, aj is element of 0, 1, 2 all the way to r minus 1. Okay, so what we saw last time was a special case of r equal to 2 where aj happened to be either 0 or 1. Okay, now it turns out that there are certain other bases which are also very relevant. Okay, we are not going to focus on arbitrary bases, for example in base 3 or base 5. It's possible, but that's not the focus of this course. So we are going to look at very special representations of r equal to 16 and at most r equal to 8. Okay, so this base, when the base is 16, it's essentially called hexadecimal. Hexa is 6, decimal is 10, so it's 16. This is called the octal representation. Okay, so a number d in base 10, okay, can be represented as a sequence of bn minus 1, bn minus 2 all the way to 0 in base 2, okay, as a binary number in base 2. It can also be represented as another set of numbers am minus 1, am minus 2 all the way to a0 in base 16. Okay, so what does this thing mean? It means that d to base 10 is going to be equal to summation j equals 0 to m minus 1, okay, aj into 16 power j. We are choosing the base r to be 16 specifically. That means aj is going to be element of aj, the digit in the hexadecimal representation could be one of 0, 1, 2, 3 all the way to 15. Okay. Now the problem is that the number 15 itself has two digits, right? It has two symbols, 1 and 5, and therefore I cannot be writing a hexadecimal number as 154. So each of these numbers, each of these hexadecimal numbers must have a meaning and value of its own, and therefore this one is going to be represented slightly differently. We will say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After that, in order to represent the remaining 5 numbers, that is 10, 11, 12, 13, 14, 15, 6 of them, I will move to letters, alphabets A, B, C, D, E and F. So each digit that I am going to use is now going to be one of 0 to 9 or A to F. Okay, with their values corresponding to 0 to 15 essentially, right? So let us look at an example. Let's take the same 251 that we did earlier. Okay, and we will see how to go about this, right? So remember what we did in the decimal to binary conversion. We said we are going to divide by 2, we are going to keep track of the quotient, and the remainder is going to be one of the digits or one of the symbols that we are going to get. Okay, so let us look at this. I will write the number here, I am going to write the quotient, I am going to write the remainder, and I am going to write the hex representation. Okay, so for example, I could get a remainder of 15, in which case I will represent it as F. Okay, this is very important. I'm going to keep track of this separate thing here, right? In the binary case, we didn't have a problem because we had to deal with only a subset of numbers 0 and 1, and therefore we didn't have to worry about extra symbols. Now in the hexadecimal number system, I have to worry about it because I'm going past 9 and I don't have numbers to represent in terms of symbols beyond 9. Therefore, I'm going to alphabets. Okay. So 251, I'm going to divide by 16, right? So if I divide by 16, the closest is what? 240, right? The quotient is, which is what? 15 times 16? I believe 15 times 16 is 240. It is 160 plus 80. Yes. Okay. And what is the remainder? It is 251 minus 240, and this remainder is therefore 11. Okay. Now what does 11 represent? 0 to 9, A is 10, B is 11. Therefore is B. Okay. Now I have a quotient of 15. Now 15 itself is less than 16, and therefore I am done. So what is 15? It is F. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. And therefore this one, the hex representation is F. Therefore 251 to base 10 is equal to F into B to base 16. Right? So what does this mean? It means it is F into 16 power 1 plus B into 16 power 0. Right? And what is F? This itself is 15 into 16 power 1 plus B is 9, 10, 11. 11 into 16 power 0. So therefore this is 15 times 16, 240 plus 11 equals 251. Right? If you remember the hexadecimal representation and the binary representation of this same number 251 to base 10, if you remember that number, I believe it was 1, 2, 3, 4, 5, 0, 1, 1, right? 8 numbers. So what I got here was F, yes, right? So one thing interesting to note is, in order to represent 251 in base 10, I needed 3 digits, 251. Okay. But the same number, if I were to represent in base 16, I just needed 2 digits, 2 symbols, F and B, right? But on the other hand, if I were to represent the number, same number 251 to base 10 in binary, I need 8 bits of information, right? So therefore, lower the base, I need more number of digits in order to capture the same information, which is not surprising because you are going in powers of the base, right? And larger the base, you cover a much larger range, right? So therefore, we could now do the same this thing. Okay, let's look at, suppose I have an n digit hexadecimal number, hex number, right? So what does this mean? I mean a n minus 1, a n minus 2 all the way to a0, right? And what is this numerically equal to? It is r, not r, I will say j equals 0 to n minus 1 aj 16 power j, right? This is a hexadecimal number. So what is the maximum and minimum value that you can represent with this? Again, this is a sum of positive numbers, right? aj is element of 0, 1, 2, 9, a, b all the way to f, one of these 16 numbers, right? 0 to whose values, decimal values are 0 to 15, right? So if I look at this, if what is the minimum value that this n digit representation hexadecimal can give us? It can happen because each of them is a positive term on the right hand side. Each term being minimum is the minimum value, and therefore the minimum value is 0. On the other hand, the max value, okay, is going to be simply all of these being the maximum value, which are all f, right? So it is 15. Every single aj, it happens aj equal to f, the number f, or it should be 15, okay, value 15, then the hexadecimal representation will attain its maximum value, and therefore this is going to be 15 into summation 16 power j, that is j equal to 0 to n minus 1, and therefore I can write this again as just 16 minus 16 power n minus 1 by 16 minus 1, and therefore you will get, these two will cancel, it will go to 16 power n minus 1. Now just go back and look at, if you had an n bit binary number, okay, which was essentially bn minus 1, bn minus 2 all the way to b0, we said the maximum value implies max value is 2 power n minus 1. Okay, now you just look at an n digit decimal number, right? That is going to be, you know, let's say dn minus 1, dn minus 2 all the way, not plus, comma, d0, okay? So this is nothing but dj 10 power j, j going from 0 to n minus 1, implies the max value okay, of this decimal representation, right? So if I, for example, if I just give you saying, look, there are 4 digits, what is the maximum value that the 4-digit number can represent in decimal? Obviously the answer is 9999, 4 nines, right? So every number should be its maximum value, and therefore the answer is going to be 9 into summation j equal to 0 to n minus 1 10 power j, which is equal to 9 into 10 power n minus 1 divided by 10 minus 1 equals 10 power n minus 1. Well, this is not surprising at all, because from school we know that if I have a 5-digit number, then the maximum value is 5 nines. If it's a 4-digit number, it has to be 4 nines, and so on, which is, for example, 4 nines is just 10,000 minus 1, right? 9,999 is 10,000 minus 1, that is 10 power 5 minus 1, right? So essentially that is the idea here. So this maximum value simply happens to be r power n minus 1, whatever the base of the number system is, or the r I am using as a radix here, right? So this is also called a radix 16 number, or a radix 8 number, radix 10 number, right? The binary is a radix 2 number, right? So essentially this hexadecimal is very useful, and I will relate it to the binary system in a while now, okay? But before that, let us also look at the octal number system. Octal number system. Okay. So what we have here is the decimal number to base 10. I am going to now represent using some number of bits, some number of digits. I can't say bits here because bits is very specific to base 2. I am going to use the word digit. Okay. I am going to write this as some octal, maybe I'll call it O for octal. No, I'll just call it C. Okay. Cn minus 1, Cn minus 2, all the way to C0. Okay. Which is now going to be j equals 0 to n minus 1 Cj 2 power j. Not 2 power j, I am sorry, it has to be 8 power j. Right. So this is the octal representation. And how do you convert this number? Again, let's take 251 as the example, right? 251, I'm going to look at the number, okay? And before that, each Cj can be one of the number 0, 1, 2, all the way to 7. Right? Any one of these symbols, it will take 0 to 7, right? 0 to the base minus 1, essentially. Okay, so therefore now I don't need to worry about alphabets like I did in the hexadecimal number system. So I can just deal with the remainder because they are the same as what we get in the decimal number system. So the number, I will look at quotient, remainder. Okay, so what do? I am trying to convert the decimal number 251 to base 10, okay, and into an octal representation, that is base 8. So what do? I divide by 8, right? I divide by 8, and therefore I can go 240, 248, right? So so 60, not 60, 30 into 8. So this is what? Maybe I get 31 and remainder is 3. Is that right? Because I get 8. Yeah, 31 times 8 is 248. And therefore I get a remainder of 3. Now I do the same procedure. I convert, divide, take 31, divide by 8. 8 3s are 24, right? And therefore the quotient is 3. And the remainder, 31 minus 24 is 7. And then I get 3 here. There's nothing more to divide. So therefore I just take this number, right? and 251 to base 10. Remember, this is the least significant bit. This is what is going to get multiplied by 8 power 0. This is 8 power 1 and this is 8 power 2, right? Is going to be 373 to base 8. Okay, so why is this correct? Let's verify this. It is 373, 8 power 0, 8 power 1, 8 power 2. Okay, so what do I get here as the multiplied? 8 power 0 into 3, which is just 3. 7 8s are 56 and 64. 8 8s are 64. 64 times 3 is 192. Right? So what do I get here? 192 plus 50 is 242. 248 plus 3 equals 251. Right? So effectively, the same number 251, which was represented using just 2 digits in hexadecimal as FB, is now being represented by 3 digits in octal 373, which also needed 8 bits in the binary representation. Okay, so this is a sort of just an overview of taking a number and representing it in base 16 and base 8. These are way more critical for us as an electronics engineer, right, than the other bases of the number system. So we will not worry about the other bases too much, right?